Good afternoon. Cameras rolling, we ready?
Yeah.
All right, show business, you know.
That's right.
All right. Recap, recall, and where we're going. Okay, so we're gonna look at some of the fundamental ideas in the first half of today, and then we're gonna transfer over to the slides, to the chapter notes, and get through those. Okay, so the approach that we're gonna be doing for the next couple weeks at least, maybe even longer, is that fundamental ideas and then just kind of filling in the gaps in what's in the chapters. Okay. If you get the big picture ideas, then you'll understand the readings a lot better. So, quick recap on what we did last time. We've been talking about the ANOVA, right, for the past couple weeks. Talking about the ANOVA, and you should be familiar with what we're doing when we're doing ANOVA, right? So, keep drawing that 3-group layout, right? What do we have here? We have data points, and we went through the logic of how we set this up, right? And why we're doing it. Remember why we're doing it, right? So we're trying to see, well, if you're an experimentalist, maybe you gave these people 1 milligrams of drugs, these people 2, and these people 3, okay? And you'd like to see if there's a mean difference. Now, what's that null hypothesis that you're evaluating in a 3-group problem like this? Well, it can be stated in different ways, as we were talking about last week, looking at the slides a little bit. But what is it experimentally? It's mu1 is equal to mu2 is equal to mu3 is equal to mu-j, depending on how many group means we have, right? So that falls right out of the experimental idea of why we would want to do the ANOVA, okay? Under the null hypothesis, what's going on here, right? Under the null hypothesis, we wouldn't really be seeing any group differences, would we? Right? Under the null hypothesis, we're kind of saying that any differences we see is due to what? Right? Any differences between points that we see, no matter what the points, it's just due to what? Yeah, just due to random error, right? Just due to random error. So you start off with this idea of saying, well, if there's nothing going on in here, then really all we should be seeing is random error. Random error, and you can call random error, another name for random error, you can kind of call it approximately equivalent to the idea of chance, or at least things that we are unaware of, right? Things that we're unaware of as to what's producing differences between the observations. Okay. So remember we went through last time, and this is important when we get into factorial ANOVA. You know, the question is, why do you think these 2 points are different from one another? And just quickly, why might these 2 points be different from one another?
Individual variability.
Yeah, individual variability. And then we say, well, what does that actually mean, individual variability? Well, it could be an infinite number of things, right? Infinite number of things that we did not control for in the study, or that we're not including in the study, right? So, in a sense, we don't really have that good of a theory as to why these 2 observations might be different. And if you do, then you're doing a bad experiment. Because if you know why this one's different than this one, and you have a really good idea, then you need to be doing factorial ANOVA to include that factor in the design. But as it stands within groups, well, random error, well, I don't know, the individual differences of which there's an infinite number of possibilities. But you do, hopefully, have a theory as to why these 2 observations are different from another, and what's 2 possibilities. One possibility is what you hope is that the people who receive 1 milligram of drugs are different than the ones who receive 2, and that's the actual theory that you're evaluating, right? That's the theory you're evaluating. Now, what's another reason as to why 1 might be different than 2? Could be just random error as well, okay? So we talked about this last time. We can look at this and say, well, that's our overall or grand mean, right? There's our grand mean of all observations. And the idea of the partition of the analysis of variance says, well, any deviation from the grand mean, right? Any deviation from the grand mean, this is a deviation from the grand mean. So for instance, this is observation I, observation 1 in group J, is different from the grand mean for 2 possible reasons. Here's one, possible reason, and here's another possible reason. Which one are we interested in? Which one did you do the study for? The first possible reason or the second one? So you look at that, you say, well, any deviation in the data from the grand mean was due to two possible sources. It has to be the partition. So which one of these two sources, this one or this one, was your purpose in doing the ANOVA, why you did it?
Second.
So how many people say second? Agree, right? Why? Because you see in the second one, what's this? This is the group mean, right? This is the group mean minus the grand mean. You're looking for the imbalance in those sample means, which should mean that there's a difference from the grand mean. So this is the one that you're doing it for, or this is the one that you're doing it for. You're doing it for this? No, because this just expresses what? Within error variability, within error variability. And see, you can look at that equation, you could talk a lot about ANOVA in there, because which one do you want to be big? You want this one to be big, right? You want this one to be big, you're cheering for this one, and you want this one to be small. Why do you want this one to be small, right? Remember, why do you want this one to be small? What? Are you biased towards this one? Why not? Why do you want this one to be small? See, it all ties together. Why?
Effect size.
What's that?
Effect size.
Okay, let's think about this now. The effect size, if this one is small, then everything is going here, right? Because of the partition, that deviations from the grand mean have to partition into this. And that's a mathematical fact, that it's the partition of the analysis of variance. It has to work out that way. It has to work out that way. So there's other reasons too as to why you'd like this one to be small. Why do you want that within variability to be small? You want this to be big, you want this one to be small. The smaller this is, the more, what does it give you for rejecting the null?
Does it give us less noise?
It gives us, you're absolutely right, it gives us less noise.
More power.
More power. Does everyone see it? Everyone on board? That more power, it gives you more power. The lower this denominator in the F test, all else equal, the more power you're gonna have for rejecting the null. Why? Because the lower MS within, right, this is all gonna translate into the F statistic. So F is MS between over MS within, and we talked about the degrees of freedom, you have to divide over and things like that. But see, this here ends up, eventually, after you divide by degrees of freedom, ends up being MS within. Right, ends up being MS within. The lower MS within is, well, then how's MS between looking? It's actually looking pretty good. It's a relative, it's a ratio, which is a comparison of two quantities that way in a relative fashion. So MS between relative to MS within. The lower this is, the better this starts to look. Therefore, this increases. And do we want big F statistics or small? We want big, because if we have a big F statistic, you know, if I get an F of, let's say, 10, let's just use a number. F is equal to 10. What do you ask that F? Ask the F a question.
What's the probability?
Yeah, what's the probability of getting something like you, right? What's the probability of getting something like you? And then the F goes, I have no idea what you're talking about. So clarify for the F. What's the probability of getting an F like this? What's the probability of getting 2 heads out of 5 flips?
Go to the distribution.
Well, we need more. I don't know what the probability of this is. This could be high, this could be low. Specify what's the condition. Right, the probability of getting an F like that is kind of like asking the question, what's the probability of 2 heads out of 5 flips? I don't know, is that high or low? Probability of 2 heads out of 5 flips, is that high, low? Nobody knows until we do what? Until we specify a null hypothesis, right? Until we specify a condition for which we would say, you know what? Let's specify where we think this should have arisen, and then we can determine the probability of it. Right? So the probability of getting an F like this under what hypothesis? The null hypothesis. Under this hypothesis here, the probability of getting the F stat that we obtained under that null hypothesis Then you compare it to the F sampling distribution for appropriate degrees of freedom, and then you locate it in the distribution. So we haven't looked at the F sampling distribution. That's more of a topic for theoretical stats, but that F looks like that. It's had a rough childhood, it's a little bit misshapen. But there's the cutoff level there, you know, and then if your F happens over here, well, then what are you doing? Well, it's further than the critical value. It's further than the critical value. And what's the critical value determined by? It's determined by the degrees of freedom. Determined by the degrees of freedom. It's the exact same logic as in the t-test, only we're not going to tables now, we're gonna do it in software, but you see what the software is doing. It's going, hey, the probability of getting an F like this under the null hypothesis, it ends up being, maybe it's pretty rare, maybe it's less than, P is less than 0.05, if that's the critical value you're using. Therefore, only 5% of the time do we observe Fs like that. Yeah.
When you, I'm gonna try to articulate this question and now have it make sense. So when you use an ANOVA statistic, are you always assuming that null hypothesis? Like is the null hypothesis set to using ANOVA?
99.99% of the time it is. But that's a good question. That you could theoretically at least operationalize this to be a different hypothesis, be a little bit harder. But the classic ANOVA hypothesis is going to assume equality of means. Yeah. But that's a good question because in some cases, I mean, it's theoretically possible. It's like those directional tests and the t-tests, right? So we assume equality, but you could try to, and it'd be harder to try to get to what the sampling distribution is under inequality. It'd be really hard, but theoretically it would be possible. Yeah. But 99.9% of the time, that's always going to be our null hypothesis. So you get your F, it lies in the rejection region, you reject your null hypothesis, and what can we conclude? Okay, what can we conclude? Well, what can you conclude with this? So you reject, right? Your F is extreme, and you reject. Just to add to that last point, any situation where you can construct a sampling distribution, then you can derive a theoretical test for. That's the key for it. So if you can derive a sampling distribution under the given null hypothesis that you're stipulating, then theoretically you should be able to derive a test for it. Okay. So there's our null hypothesis, you reject it. Conclusion, what do we conclude? So what are we going to conclude from this? Conclude? Let's get a conclusion on that. Be a good conclusion, yeah.
mu1 does not equal mu2.
Okay, so, well, is mu1 not equal to mu2? Well, maybe. Or maybe mu2 is not equal to mu3. Maybe there's something going on in here, right? Maybe there's something going on. So the rejection of the null basically tells us you might have something going on between the means, right? You might have something going on between the means, but it does not tell us where those differences may be, right? It tells us you may want to look at those means a little bit more to try to see where the differences are, right? Now, recognize that these here, again, these are what? Population means. These are population means. Those are mu's, population means. What are these? When you get your data from this, you getting population means? No, there's mean 1, there's mean 2, and there's mean 3, right? There's mean 3. So when you look at your F-stat, what's your F-stat doing? It's comparing MS between to MS within. It's using sample means to get that estimate, right? It's using sample means to get that estimate. But do you expect differences between sample means? Yes, absolutely. Look, if you didn't get differences between sample means, do you need to go over and do your F-stat? No, you don't need to. Okay, question on the test, 4.6, 4.6, game over, right? Game over. What about power? Game over. Collect a billion observations. If it's 4.6 and 4.6, there's nothing going on in that numerator. Nothing going on in the numerator. So mean 1 equals to mean 2 is equal to mean 3. We expect these to be different. The question is, are these different enough, right, that we can make a conclusion that this statement no longer holds, right? That this statement no longer holds. But remember, in your sample data, I mean, almost always, unless you're dealing with really, really simple data, you're gonna get a difference. You're gonna get a difference, but that's not the point. That's not the point. So, look, we put this in context a little bit. Let's say your means came out to be, let's say your sample means came out to be, I'm just gonna make sleep hours, right? So 2, 6, 12, give them a lot of melatonin, a lot of sleep aid, right? And they're gonna sleep forever. Give them 1 milligram, they're gonna sleep 2 hours, right? You look at this, sample means, right? Sample means. Now let me ask the statistical question. Do you think this is gonna lead to the rejection of the null? Do you think this is gonna lead to the rejection of the null? I mean, what do we think as experimentalists? Do you think it's probably going to? And if we're not sure, why would we be sure? I'm gonna say 2 versus 6, 2 hours, 6 hours, 12. I mean, let's make it even more extreme. These people just don't get up. Okay, these people are 20, okay? Laziness is not a confound, we've controlled for that. So 2, 6, and 20, and I'm gonna suggest, boy, well, I don't have to do a statistical test. Just reject the darn thing. What do you think? You lost the stats book, you lost the stats program, and you say, you know what, there has to be, look at the size of the mean differences. Just reject the null. What am I missing? I'm missing something in my understanding. What is it?
You can't directly compare sample means to population.
I cannot compare sample means to population means. You're absolutely right, but I'm kind of saying that wouldn't it be pretty safe? I mean, look, it's just a big difference. After all, that's all I'm looking for is mean differences. The size of the mean difference is huge, 2 versus 6 versus 20. Just reject the null. What's missing from, is it possible, here's the question, is it possible that you obtain sample means like this, but you're still unable to reject this? Yeah.
There might also be a lot of within variability.
There might be a lot of within going on, right? There might be a lot of within. Until you actually, I mean, you can visualize the data, you can look at it, but to get a formal test, I mean, under what circumstance would your ANOVA go, you think you got a difference going on? You know, it comes back and goes, nope. You analyze your data, it's like, you've got to be kidding me. What might the data look like? Maybe you've got so much noise in there that what you're seeing is best explained as just noise. Right? Is best explained as just noise. Does that make sense? That's the rationale, right? That's the reason why we're doing that F test, is to compare that between to within. Now, you lose your stats book, you lose your stats program, you can do the ANOVA, not even arithmetically, you can look at things and kind of figure things out. How would you look at it? You get your data, if it's not too big, it's not like billions of observations, you look at it, what do you try to look for? First of all, if all these people have 2, and all these people have 6, and all these people have 20, slam dunk. 2, 3, 2, 4, 2, 6, 5, 6, 5, 6, 4, 21, 19, 18, 17. You see it. You say, I know how this is going to turn out. Okay? So remember that between to within. Okay, now we said, well, this isn't enough. This is enough. You get your F-stat, but we know there's problems with inferential statistics. There's problems with this. I mean, it's an okay statement to make, but we know from all this stuff that P is less than 0.05 can happen due to what? What's the big influence of it? Right, sample size. You get enough of a sample size, so long as there is difference in your sample means, you're guaranteed to reject. It has to happen. It has to happen, so long as there's difference in your sample means. If there's no difference in your sample means, you can't reject. Right? You can't reject. Why? Because the numerator is going to equal 0. So you can't just up your sample size if your sample means are equal and hope to reject, because they'll never happen. But how often are these going to be equal? These are going to be different. So this is practically, for 99.9% of the cases, that's a guarantee. That's a guarantee. So the statement comes out of the lab report and says P is less than 0.05. Your response is, what do you say? You say P is less than 0.05, you say what? Say what? Not enough to know if there's a scientific effect going on, because this is simply for an inferential statement, right? So then we said, well, how is expected to know what's going on? If MS between to MS within is not telling us the full story, then what can we use analogous to Cohen's d? Eta squared. We go to eta squared, and why are we going to eta squared? We're going to eta squared because, look, nowhere in eta squared have we crossed the boundary of degrees of freedom, right? We haven't divided by degrees of freedom yet. So this is just giving us those raw sums of squares. This is just giving us the raw sums of squares for which you can say, hey, is SS between and SS total influenced by n? You know, are these two quantities versus p-value, is this influenced by sample size? If I increase my sample size from 100 to 100 million, what's gonna happen to eta squared? Is it gonna naturally just keep going up? Is it naturally gonna keep going down? What's gonna happen to it? Might go up, might go down, right? But basically it's going to reflect, right? What's it gonna reflect? What's eta squared gonna reflect? It's hopefully gonna reflect the scientific effect. Hey, between stuff bigger than the total stuff, but nowhere in there is sample size having that kind of influential factor as it is here for the inferential test. This is the logic of why we look at eta squared, why we look at Cohen's d, right? Why we look at that. So we look at that, and let's say our value comes out to be 0.90. Okay, so interpretation, your eta squared comes out to be 0.90. Interpret, how do we interpret that? Well, is it big, small? Is your eta squared of 0.90 big or small? Well, it depends, right? It depends. You can't evaluate that in a vacuum. You can't evaluate it in a vacuum. Now, 0.90 and you reject your null hypothesis, still doesn't mean this is big or small. Right? So there's the final exam, right? Perfect question. You got 0.90. Hey, you want to know if it's big or small? Just do your inferential test for the F, and then you'll say, well, if P is less than 0.5 and 0.90, I must have a huge effect size. No, not necessarily the case. If everybody else in your field for the area is finding 0.99, this is actually very, very small. Does it make sense? This idea of effect sizes makes good sense, right? That's really, really important. I can't tell you how important that is, because you see researchers going P is less than 0.05 and getting all happy about it, and then they compute their effect size, but the effect size may actually not be that big. So this has to be compared to the context of what you're studying, right? A lot of effect sizes in physics, they look at 0.90 and they absolutely laugh at it, because they're used to really, really high, just based on the material they're dealing with, very high effect sizes. Where in other cases, you know, trying to help human populations and stuff like that, like very, very valuable research, sometimes your effect sizes, your eta squared, is only about like 0.30, 0.25. Yeah.
Is your effect size directly altered by your power?
Okay, good question. Let's open that up to the class. Is effect size related to power? Is effect size related to power? So let's say your power is, you know, 0.5. Let's say your power is 0.9. What do we expect that effect size to do? Can I compute effect size on 5 observations? Yeah, technically I can, right? So let's say I compute on 5 observations and I get 0.90. So I go n on 5 observations and I get eta squared is equal to 0.90. What does power have to do with this? Where's the power in here? There's the practice, right? As you put things in different contexts, then you'll be able to interpret an experimental result. N is equal to 5. What our test started doing, we more in the final. N is equal to 5. Eta squared is equal to, hey, what about power? What about power? Where's power fit into this?
Power might be small because it's a small sample size, so you may not have the p-value to detect the difference that the effect size might indicate.
Okay, so yeah, exactly. What she said is like power it's probably gonna be really, really low. So, I don't know, effect size of 0.90 is absolutely true based on these observations. Eta squared is doing what eta squared, that'd be a really small sample size, but eta squared is doing what eta squared is doing, right? Maybe we just wanna like increase that a little bit, like at least have like, say 5 per group or something. So we have 0.90, n is equal to 15. Eta squared is reflecting this, but what are you missing? That's where, I come across as being mean to the p-value. Like, what do you have against the p-value? I really don't have anything against it. But here's where you go, wait a minute now. Somebody at the conference, at the APA conference go, eta squared 90%. I just explained 90% of the variance. My sample size was 15, that's where you say, do you have any inferential support for this? And they say no, because p-values don't really matter, it's effect size. What do you say? Effect size is what matters. Get with the times, they say, right? P-values are like so outdated, okay? So what do you say? You say, what? I mean, what's the problem with this, right? Hey, I explained 90% of the variance. You reduce the sample size. It doesn't quite work for effect size because eventually, like, you have no observations in the group. But let's go down to like this. N is equal to 3. I did an experiment with 3 objects, and I got 90% variance explained. What's the problem? Forget the stats book. Forget it. Forget the course. Just think of that. What would you say? You'd say, wait a minute now, please collect more observations. I did a survey to see who would vote Republican or Democrat, and the first 3 people said Democrat. I guess everyone's gonna vote Democrat. You say, wait a minute now. You only asked 3 people. Your effect is huge because you got all 3 Democrat versus 0 Republican, but please collect more observations so we can get a little bit of a better picture, right? So this may be telling you what's true about the n is equal to 3, but you wanna get more of a sample size. That is your inner p-value, right? That's your inner p-value going, you're gonna need more here. Does that make sense? Make these things a little bit human, right? The p-value is going, I'm not happy with that. Consult with the p-value. You okay with it? No, I'm not okay. Because what's your p-value gonna come out to be? Sure as heck isn't gonna be less than 0.05. It might even actually be a bit low, like 0.30, but it's gonna say, get some more. So you collect more observations. What happens to this? Case scenario on the final, n is equal to 4, 5, 6, 7. What happens to this? As that sample size increases. Whatever happens to it, right? It's kind of like, I don't know, what do the data have to say? What do the data have to say? So, depending on the material you're dealing with, if you're a knowledgeable researcher in the area, you've got to know the substance of what you're talking about. The research area, the statistics won't tell you everything. So you look at this and say, wait a minute now, typical effect sizes in this area is 0.60. You're getting 0.90 on 3 observations, you've just gotten lucky. Keep collecting data and I bet you that effect size is gonna drop. Because these 3 observations are just luck of the draw. You surveyed 3 people, you got lucky, keep going. Therefore, in that case, your sample size increases and your effect size drops, and it eventually seems to stabilize as you collect more and more of a sample size. Does that make sense? Does that concept make sense? So you see how what's at work there is the p-value. Whether we call it the p-value or whether we just recognize the role of what the p-value is doing, this is saying, give me some inferential support for this. So in a sense, the p-value, one of the jobs of the p-value is saying, do you have actually adequate sample size to make an inferential statement? Because if you don't, then that effect size is kind of, it's impressive, but it's just not based on very much information. Does that make sense? Effect size versus p-value. Now, let's extend this a little bit, talk about omega squared, also in the notes and in Montgomery. This here turns out is a little bit biased, okay? And there's reasons why it's biased that don't really need to concern us, but the eta squared is a little bit optimistic. It's a bit optimistic. So it tends to overestimate the actual effect in the population a little bit. So we can say that eta squared is too optimistic. That's not gonna work, optimistic, Okay, it's optimistic overestimate. Okay, if the true effect size is like 0.80, well, maybe eta squared is going 0.85 or something like that, a little bit too high. So another statistic has been suggested, and that's been in use for many years. It's the omega squared statistic. The omega squared statistic is a measure of effect size, analogous to eta squared. Eta squared is an effect size. Omega squared is an effect size. But it's a little bit less optimistic. Okay, it's a little bit less biased. And if we look at the spelling for it, we can kind of see why it's a little bit better estimate of the population effect than eta. I mean, why would that be? So omega squared, better estimate of population effect. It's a better estimate of population effect. What's the true effect in the population? Omega squared is better than eta squared. Why? Well, we'd have to go through the proof of that, which would be really, really ugly, but we can look at the formula and get a feel for it, right? Why would that maybe be a better estimate, a better kind of inferential idea of what's going on in the population? We'll just compare the formulas. You got SS between. What do you got here? Eta squared, SS between. Okay, so you have MS within, you have SS total, MS within. What's the difference here? Well, this is SS total. What does this formula do that this formula doesn't? Big picture wise.
Degrees of freedom.
Degrees of freedom, and even more important than that, you're absolutely right, degrees of freedom, and what this omega person tries to do is say, you know what? Let's throw on some inference on here. Let's allow the crossing of those degrees of freedom. We've divided by degrees of freedom, and let's put in some of those MS within values. Because when you're thinking about MS within values, what do we know MS within gets into? When you think F, you're thinking inference, right? You're thinking, wait a minute, F is an inferential statistic. Eta squared, we didn't divide by degrees of freedom yet. So you can appreciate that omega squared is trying to give you a better estimate of what the true population effect is, right? What the true population effect is, and to do that, it had to go and get some MS within values. And where the MS within values come from, they're coming from your ANOVA, so it kind of put those in there. And many people would like to see omegas in research reports because it's a little bit less biased. We can spend all day comparing omega squared to eta squared. Practically, for our purposes in terms of reporting these things, you're probably going to want to go to omega squared when you report them for your ANOVA. Now, having said that, a lot of people really like the eta squared too. The eta squared is very, very intuitive. It has that direct ratio appeal of SS between to SS total. We recognize that some journals and some of your supervisors will want to go to omega. Let's talk about the model equations. Okay, we've talked about this a little bit, but we have to talk about it a little bit more. We have this here, the partition. So deviation from the grand mean is equal to 2 parts. Well, what's the big picture of what we're formulating here? We looked at it a bit on the slides. We have a model equation right here for the analysis of variance. Now that model equation, what's it actually telling us? Model equations, for what reason are we having model equations? We're trying to theorize what a given observation is made up of. We're trying to get a theory. That's what a model equation is. What's the theory as to why I, J? Individual I in group J. How did this person or this observation arise? Okay. How did this person arise? So what does this represent? This represents any data point in your data, right? Because it could be individual I, individual 1 in group 3. That's one individual, one case. Here's another case, etc. So what the model equation is saying is that individual I in group J is a function of what? Right, is a function of what? The equal sign, you can read it as saying as a function of, like, similar as to if you take x and y and you draw a line, that's a function, and we can say what? Y is a function of x. If x is equal to whatever number here, well, y is equal to that number, right? Make sense? That's just a little bit more of a complicated function that has more ingredients to it, has more ingredients. So it makes sense, right? Model equation, you're gonna see these forever in research and statistics. You'll wanna know what's the model equation. You get to regression, you say, well, what's the model equation? Y sub ij is equal to, well, what's this? Mu. Well, it's population model equation. So this is for the population. So it's saying that any given observation in your data can be theorized to be a function of the overall mean, right? The overall mean, that's mu. So the overall mean of your data. And if that was the only thing we had for our model equation, how satisfying would that be? You know, if the population mean was the only thing we include in our model, imagine if we just stopped it right here. But why, you say, you want to theorize about the observations in your data? It's composed of the overall mean of the population. How much would that happen? What would that imply about this data here? What would that imply about this data? If the only thing we have to go by is that any observation should be equal to the overall population mean, what would that imply about all these observations? They're equal. Does everyone see that? If this was the only part of our model equation, ij is equal to mu, the population mean, that'd mean that, well, everybody's equal, calculate the mean of everybody, and that's the mean of everything. Right, that's the mean of everything. So if ever you see a model equation that says, you know, we're gonna do some sophisticated modeling on our data, and we're gonna theorize that any observation in our data is equal to the overall mean, wow, that's a pretty boring model. That's a pretty boring model because we could have told you that without anything. We just say, just calculate the mean of all the data. What's the next part there? What's the next part? So recognize that's the first part, not very exciting. What's the next part? The next part is the alpha j. The alpha j, we talked about it last week or the week before. These are the AJs, right? These are the AJs. What's an AJ? The sample equivalent of this population parameter is this. There's the little AJ. These are the sample equivalents down here. What's the AJ? Well, the AJ we said is what? The treatment effect, the sample effect, sometimes it's called. And how do you define the AJ? Reference to that table. Right? So what are these? Sample effects. Well, I'm gonna say this is the population effect because that's for population data. Population effects. This would correspond to sample effects because they're in the sample. You can also call them treatment effects, okay? Treatment effects. What do you call them treatment effects? Yeah, treatment effects is trying to say, well, does your treatment have an effect? That comes from the experimental idea, right? As soon as you get out of the abstractness, you say, well, we're actually applying different treatments to different groups. So they're sample effects, the effects in your sample, but they're actually treatment effects because you're treating this group different from this group. So you've got population effects, you've got sample effects. Is this of interest to us? I mean, this is not exciting. This is like saying that you're, you know, what some writers on this say that the overall mean just says you're analyzing a certain group of people. But this, why is this interesting? This one or its sample equivalent, why is that of interest to us? That's why you did the study. You did it for the AJs. You know, someone asked you in the hallway, why are you doing ANOVA? AJs. I'm doing it for the AJs. Aren't you doing it for the overall mean? Not interesting. The overall mean's not interesting. I'm doing it for the AJs. Okay, give me an example of an AJ. A sub J, abbreviated to AJs. Give me an example of the AJ. Give me an example of an AJ. Give me one. 20 minus the overall mean. There's an AJ. 6 minus the overall mean, right? 2 minus the overall mean. This is what you're interested in. We want the AJs, okay? So that's a second source in this model equation theorizing how the heck did an observation arise? Like what's an observation a function of in your data? Doing it for the AJs. What's left? Another source, right? You got this overall mean, AJs. Why we're doing it? What's this? The error. That's the error, right? That's the E sub ij. What does that represent? E sub ij. What's the ij stand for again? Yeah, individual I in group J. Remember in Montgomery, he does it backwards. He goes Ji. The I refers to the group and the J refers to the object. But we're doing it as 97% of people do. Ij goes from the inside to the outside. Individual I in group 3. Individual I in group 2. So let's ask ourselves, what does this represent? What does this represent? Based on what we've talked about here. Yeah, it's kind of like that uncertainty, right? Like that randomness or that, I don't know why they're different, it's just due to error. And remember this idea of error, calling it an error doesn't imply it's a mistake, it's just the unexplainable part of our data. The part that we're actually not trying to explain, I don't know why these two are different. I have an idea as to why these two are different, but it could also just be due to the E, right? This difference here could be due to the E. This difference here could be due to the E. But this difference here between groups, I have a theory for it. Where is it in the model equation? Yeah, everyone see it? This one versus this one is reflected. I have, there's two theories as to why this observation might be different from this one in that equation. Where are they? AJs and the EIJ. Which one are we cheering for? AJs, right? We're cheering for the AJs. Give me the ultimate scenario for that model equation if it works out for your data. Imagine you worked out for your data, you analyze your data, and you're able to reduce this model equation. It worked out so well that you're able to reduce this down to something that's absolutely perfect for your scientific investigation. What term in there would go right to 0? The E. Does everyone see it? The E would go to 0, and you can see how that'd be reflected. All 2s, all 6s, all 20s. My goodness, you get an experiment like that, you're not even dealing with physics, because they still have an error term, but this goes to 0, you say, you know what? Error term not needed. I've got a handle on this material so well that I'm not seeing any within variability. It's all between the ultimate experiment, at which point your ANOVA would have a hard time calculating anything because it won't be able to get the denominator, but you wouldn't need it. You'd say, oh my goodness, this works out perfectly. So this EIJ reflects what? Reflects the mess, reflects the uncertainty. Statistics is born because of this. Statistics was born because of this, to try to get a handle on this and still make some sense out of things. So there's your uncertainty over there, is in the IJ. The lower part are the sample equivalents. So here's your population model equation. Here is your sample model equation. And you can see how they're the same except for notation. Okay, you see how they're the same? Does everyone see it? You got the small AJ. AJ, what's this AJ represent? There's your treatment effects, sample effects. That's dealing with your actual data. What are we using these numbers to correspond to? To estimate the population effects. To estimate the population effects. You're getting this from your sample data. What you really want to know is this in the population. Make sense? Now, model equations are really important. We spend some time on it here because as we go on to the factorial analysis of variance and complicate the model equation is going to change. So let me just preview where that's going to go. So imagine for this data, not only do you have a theory that melatonin differences are going to be apparent, But you have a theory that age is gonna be different. Because you can control for age in here, let's say. This person here is 50, this person here is 18. I don't think we can give melatonin to kids. So this person here is 25, etc. How do you put your second theory in here? You got the melatonin theory. Where's the second one go? Well, maybe you do something like this. Say, you know what? Based on my expertise as a researcher, you guys have to be the expert in the area. You have to say, well, I think there's an age effect too. Let me do this. All these people, age, less than 40, here, greater than 40. Two sources of systematic variation that you're trying to see if something's going on. Does everyone see it? This here, where you have two sources now, you have, well, the one source is the melatonin, the other source is the age. You're gonna put them both in the same experiment. That's called a factorial ANOVA. A factorial ANOVA. Let's look at our model equation for a second. Now that we're on the model equation, I asked someone to kind of like, how are you gonna reflect that in here now? Yeah, just go with the population. Well, we know that this is the sample one, but they're just corresponding to one another. So look at that population equation. And how would you reflect that other factor? We have one factor in there, we've got the ages. How would you reflect this new factor? Everyone see why we included this? And I grouped them into age less than 40, right? I didn't just like arbitrarily say, you guys are gonna be less than 40. I can't do the experiment, which is a problem. Ideally, what would be the best case scenario? You're gonna be 40, you're gonna be 40, you're gonna be 40, but we can't do it, so conclusions are gonna be difficult because we have to take people as they are. But there's my age group. Reflecting the model equation. What are we gonna do? Why would this be, here's the question is, why would this first model be inadequate to analyze this new setup now where we have an age factor?
Are we assuming equal numbers in each?
Sure, yeah, let's assume equal numbers per cell, right? So we got now cells, there's one cell, there's another one, there's another one. Let's assume equal numbers per cell. Not totally vital for the model equation, but that's okay. Let's assume they're all there. I'm gonna play it naively and I'm gonna say, well, I'm just gonna go with this model equation. I'm still going to use this model equation to reflect this. Still gonna use that model equation to reflect that. It's worked for me before. AJs, getting to know the AJs. So what I included a second factor, I'm still gonna use that equation to reflect this. What's the problem? What's the problem with that? Okay, well you say, well the problem is you're not accounting for this factor, and I say, I don't care. I just wanna do it this way. It's the issue. Where is this factor in there? Does everyone see it? So the question is, I added the age factor, said you guys go here, you guys go here. My purpose statistically, methodologically, research-wise, in doing that is to do what? To get to know more about what thing in that equation. This, right? I'm trying to unpack the error term. I'm trying to unpack the error term. I'm trying to say, you know what? That error term is actually pretty high. That tells me what? There's more to know. There's more to know in determining values for y, because I have actually maybe a pretty big error term. So what I've done here is I've systematically added another factor, factorial ANOVA, into my design, but the purpose of it, is it to get to know more about the AJs? No, I know about the AJs. They're right here. It's to unpack the error term. So if I'm gonna unpack the error term, why, this model's not gonna do it. This model's not, I need more, so what can I do? What can I do for the model? Well, I'm gonna make some space here. Gonna say plus, and then I'm gonna go over here. I'm gonna still put the EIJ, but we're gonna have to add some things to this. So what else can I add to my model equation that would reflect that process? Well, AJ's in this case represents column differences in columns. So what's my, we need another parameter there to reflect what? Exactly, the differences in rows. The differences in rows, okay, the differences in rows. So, I use slightly different notation in the chapter, I'm just realizing how I set this up, that's okay, we'll talk about that. Generalization will not be hard. We're gonna go beta K. Beta K. AJ's, beta K's. Both are Greek letters, they're just used to show those parameters, beta K. Well, the beta K is going to reflect whether you're in this level of the factor. You see how I'm using these terms, right? Level of the factor here, or this level of the factor. The A sub j in this level of the factor, and the beta in this level or this level. Make sense? Yeah. So I've got two sources of variation reflected. I still have this error term sitting out here. I gotta add something to it. Why do I still need the error? Do I still need the error term? Yeah, why?
There still could be unclaimed.
There could still be error. Where's the error happening now in this design?
It could be happening now.
Yeah, let's think about it, right? Well, it could be happening basically everywhere, but this particular term here that I'm adding, I mean, look, if the columns explain everything, and this explains everything, I'm still missing one source. But eventually I'm gonna say, well, plus EIJ, what else do I need? Another subscript?
Okay.
K. Okay, so EIJK. EIJK, because now the unexplained variation in my design is happening where? Not within these groups, but within what? The cells, or these smaller groups if you want. There's a cell, there's a cell, there's a cell, another one, another one, another one. It's now within the cell, right, within these cells, where the unexplained variability is happening. So when we ask you, say, hey, why is this observation different from this one? What do you say? Say, I don't know why, right? Why? And I say, why don't you know why? Did you do an experiment? You say, yeah, we did the experiment, but look, they all received 2, right? They all received 2. They're greater than 40. Actually, maybe that might have something to do with it. We're missing a term. But within the cell, I don't know, not quite sure. The within cell variability is reflected by the error term. Now I left this out here. Plus, there's another source of variability. There's another source of variability that we still haven't put in here. So the model's getting a little bit complicated. What's the other source of variability? Think about it. Yeah, just stop and think about it, right? You got the A, this refers to, well, in this example, it's the columns. Okay, we're gonna switch it to rows in a second. I started off with columns, we'll switch it to rows, it doesn't really matter. This one here, columns, rows. There's another source of variability that's not just random error. We can see that there's still random error. But there's another source of variability in here that we can kind of say, wait a minute. Looking at the A's, looking at the B's is not enough. There's another source. Where's the other source? It can describe it in the design. No, we also want to use a word for it. I know where you're going, somebody knows, right? Why is this observation different from this one? Yeah, difference in cells, right? Difference in cells. When we put this other factor, the H factor, not only have we introduced the BKs, not only have we introduced the ding, right, you got it, right? Not only have we introduced the BKs, which would say, well, maybe there's an age difference, right? The AJs are accounting for melatonin differences, the BKs are accounting for age differences, but what's accounting for this? The cells. What's accounting for the cells? The AJs accounting for the columns, the BKs accounting for the rows, right? But what's accounting for the cell difference? Well, what is it? Maybe it has to do with being in 2 milligrams and yeah, you got it, you got it. You're in the 2 milligram group, and you say, why am I sleeping so much? Right? Why am I sleeping so much? I was in the experiment, my goodness, I slept and slept and slept. You ask the experimenter, why? And the experimenter says, we analyzed the data. You know what it is? It's due in part to the melatonin we give you. This is what you're saying at the conference or something, right? The people who receive more melatonin, they actually sleep longer. How is that influenced by age? Well, we looked at that too. The people who are older sleep longer, but there's a relation going on with the melatonin idea. So it could be that what's really mattering here is the cell to cell difference, and that has to do with, what are these? These are kind of like crossings, right? Melatonin by age. Melatonin represented in this design as AJ by B, J, K, by JK. What does that represent? The crossing of the factors. The crossing of the factors that lets you know maybe there's something going on in the cell, and not just the rows or the columns. Not just the rows or the columns, but something going on in the cells. Make some sense? Yeah.
So is that, that's still an error, still a value of error, is it not?
Okay, good question. Well, you got in this particular design, you got the row, column, row, something to do with the cells. We're gonna define this as what? What's this gonna be defined as pretty soon? Starts with an I. Interaction. Interaction. What all science is about is interactions. What's this? What's the error term for the experimentalist, right? What's the error term for the experimentalist? You wanna humanize it? What's the error term for the experimentalist? They see the error term come out of their output, and what's that? The error term is humility.
Yeah.
Does everyone say it? Say, ha, nice try. You still don't know what's going on fully. You may have a handle on this, a handle on this, a handle on this, but God still rules, right? That's kind of like saying, you don't know why those two observations are different. Maybe it's just due to flip of a coin. Maybe it's a roll of random of the die. You still can't explain why this person got 7 hours of sleep and the next one got 7.2. Good luck, go figure it out. Right, that's what science is. Go see if you can model that. Go see if you can figure that out. So you see that error term most likely still exists unless you've got your experiment is like unbelievably good. Say no error, it's all explained by rows, columns, and interaction. But that's still gonna exist. So then, what's the next step in this? I mean, just to forecast where we're going, we're gonna stop at this model here, but what's the next one you can do? You can say add another factor, right? So let's think of this as deterministic science. The theoretical physicists don't think like this anymore because they're actually they're finding out that there's apparently real chance and that not everything is determined. But we still behave this way in statistical models. So the idea is saying, if you want to know what an observation is in your data, which one are you going to unpack further? Unpack your error term. Keep unpacking it until how many factors are you going to have? Right? Unpack into what? an infinite number of, we're gonna run out of letters, A, B, C, D, etc., until how long is your equation? It's like infinitely long. Then you'll say, I know why you slept 7 hours, right? Because you took those stairs yesterday instead of those, right? You drive a Ford, you drive a Honda, and when you turn the ignition on the Ford, it's a little bit harder than on the Honda. Made you a little bit tired, right? You drink Budweiser, you drink German beer, right? Differences. So if you had all those differences and your equation was infinitely long, you might actually be able to say at the conference, I know exactly why this one is what it is. And then what does your audience say? You say, well, I got this infinite equation, it's too big to bring here. You say, I got it at home, it's too big to represent here on the PowerPoint. So then what does your audience say? So I gotta figure out, so I've got like 10 million independent variables, 10 million predictors. What does the audience say? They say, wow, that's impressive.
No.
What do they say?
You're crazy.
They say, truck it over here, get it on a transport and truck it over, we wanna have a look at it. What do they say? What's the principle? What says that old Greek person back in ancient Greece? Something to do with like this? What is it? What's the principle? Is it? Occam's razor, right? Occam's razor, what does Occam's razor says? Is it Occam? It might be Occam, I forget. Occam's razor, that's the principle of, what's the word? The principle is, starts with P? Parsimony. Parsimony. The principle of parsimony, what's the principle of parsimony says? Explain it in simpler ways than more complex ways. And if you have that infinite number of factors that contribute to that variable, you're actually not doing anything of interest anyways. Because the objective of science is what? Reduce it down, right? That's what I like to say. And it actually shows up on formal papers when people write papers for me. I say, you can't actually write that in the paper, but look for the heavy hitters, right? Look for the heavy hitters. What are the heavy hitters now? Is sleep a function of melatonin dose? Is it a function of age? The fact that someone's turning the key on a Ford versus Honda probably accounts for so much of what? Right? So much of this type of stuff that it's negligible, get us the big stuff, right? So as a clinician, you're doing the same thing. Someone comes into your practice and you're trying to assess the risk of suicide. What are you gonna ask them? Are you gonna say, what kind of cereal do you eat? Probably not. You're gonna say, well, what's your genetic history? Have any of your parents committed suicide? What's going on in your life right now? When you get those, what do you call those in clinical psychology? I often call them by the name of, it starts with R. Risk factors, right? What are the risk factors? Statistically, the risk factors, AJ, BK, what are those big factors that helps us know suicide risk? That helps us know how much you're gonna sleep. And that's the big idea. That's the big idea. So you want a few of them, but at some point, like look, in this model here, if the BKs, right, if age was negligible, it didn't really matter. You found out, you did your study, you say, you know what, whether you're under 40, over 40, you're just gonna sleep about the same amount, then what do you do to the model? You know, if this explains like 0.01% variance, and this explains 70%, 0.01, get rid of it. Get rid of the BKs. Look for another factor, but get rid of the BKs because most of the oomph is coming from the AJs. BKs are kind of irrelevant. Even though what's gonna happen is overall in your model, it's actually gonna increase the amount of variance explained because you've added another factor, but you're in the end gonna say it's just not really worth it. It's not really worth it. No one's gonna be impressed at the conference, right? So if someone at the conference is saying, I added another factor to my design and it accounts for another 1%, right? Which sometimes happens, you see people presenting that. fair question is, goes 1% really worth it? You're really gonna, maybe that's not bad, but you're really gonna like what, collect data on them just to explain 1% of the variance? Why don't you just take that 1% and put it where? Just put it back in the error term. Put it back in the error term. Focus on something more important. Focus on, see where the idea of effect size comes in too, right? You say, well, we can explain 1% of the variance based on age group. You say, yeah, well, we can explain 20% more based on geographical region. So that's not really relevant. Yeah.
So is there a normal, like an accepted practice for how many factors
Yeah.
to use then?
Good question. How many factors should you use, right? So, you know, the definition here, we got this a factor, that's a factor. Factorial ANOVA looks at this combination of factors in one model equation. How many factors? I mean, that's a good question. How many factors? Well, let's stop short of infinity, because that's not going to be possible. So let's bring it back. Bring it back from infinity, 10, 9, 8, 7. How many would you suggest? Ideas? See, notice the AJs are reflecting the melatonin differences, the BKs the age. So if I were to put another factor in here, where would it go? This is where we're restricted by three-dimensional space. It gets hard, right? Where do I put the third factor? That's stuck, right? So what do I have to do? If I put a third factor, what's the other factor? Male versus female. Can't put it in there. So what am I gonna have to do? I'm gonna have to say, well, these are males, and then I'm gonna have to draw another table and go female, melatonin, age, and do that. My third factor is represented by this grid for males and this grid for females. Everyone see it? That's the only way to do it, otherwise I don't have an axis that goes out like this and look at this and kind of that hyperdimensional space where I can actually see. So I have to do it like this on the board. So there I would have one factor, another factor, what we call the three-way ANOVA. Then we say, why stop there? Where's the next factor gonna go? Yeah, then look what I have to do, right? I have to go, okay, so I've got all of this, right? For level 1, Arkansas, Montana. I've added another factor, it's become a 4-way ANOVA. How many factors should you have? The original question was, how many factors should you have?
Does it depend on how many variables you're testing?
I think it depends on how many variables, but also, look how complicated it gets. Good luck trying to interpret a 4-way ANOVA, right? 4-way ANOVA is gonna contain a lot of these interaction terms. It's gonna be very complicated to figure out. And if those last factors are not accounting for much variability, you're probably just fine just getting rid of them. Because most of the time, we just don't care about things that explain such low proportions. But the 4-way, you definitely don't wanna do 5-way. 3-way, maybe. 4-way, probably not. You're looking at like 3-way, 2 ways. To be a good experimental scientist, try to explain things with maximum 2 to 3 factors. Go higher from there if you have to, but the lesser, the better, okay? Recognize too, when we're talking about this modeling idea, I mean, something happens when people are learning statistics in a scientific field like this, where, I mean, if you can explain things, you know, is there any embarrassment? There's advanced statistical models out there, and then there are so-called simpler ones. T-test versus multi-level hierarchical model. So if someone says to you, you know, I've had to do a model that involved like all these really, really weird factors, and it's huge. I needed extra computing time, it's so complicated, but I think I've explained 30% of the variance. Who's the better scientist, the person who can do that, or the person who can explain 30% of the variance based on the t-test? The t-test, does everyone appreciate that? The t-test, okay? Don't associate statistical complexity with scientific sophistication, because if you can explain it with a t-test, if you can say, you know what, you do all that, that's very interesting, it's very statistically interesting, but look, I can do this, plus this 2-group problem explains 90%, wow. No one at the conference is gonna say, yeah, but you didn't run the latest statistical model, say they need it. I didn't even need the stats textbook. If you're a good scientist, the stats textbook goes into the garbage. Because if you're a really, really good scientist, this goes towards where? Towards zero, right? That's really, really important to remember. It's often an inverse relation, not always, but often an inverse relationship with things like that, that if you really got to handle. You know, if I'm studying sleep time and I'm figuring out, actually, it's the side of the bed you sleep on, and that explains 90%. Wow. Rather than have to get a lot more factors.
So do you actually use the level of error in your decision to?
You can,
factorialize?
yeah, you can. I mean, that's a nice idea. Look, if your MS error is really big, right? If you look at your MS error, and the advanced models that we look at in the spring actually feature some of that. You look at your MS error and you say, you know what, there's more error to unpack, right? There's more error to unpack, then that may serve as a justification for trying out a few new factors. So this big idea here is the factorial analysis of variance extends on that simpler analysis of variance. Okay? So let's return a little bit. That's where we're headed, and we'll survey some of that in the notes of where we're going with the factorial. We've gone over the concepts. Let's just go back and ask the question again as to, over here we have our null hypothesis, but we said that the rejection of the null says there's a difference somewhere in here. So could be between mean 1 and 2, 2 and 3, we're not quite sure. So the question is, how are we going to do a post-investigation into our rejected null? Okay, so how are we going to do a post-investigation into our rejected null? So the idea is that you've rejected HO in ANOVA. We'll go back to the one-way ANOVA, one independent variable. Okay, so for now, one-way ANOVA, that's that one independent variable. Just the one factor, like just the melatonin. So you reject HO, different ways of saying HO, but here's the thing you're really interested in as experimentalists. It's rejected. So what could we do? What could we do? Well, here's the thing. We get into this idea. Is it up there? Nope, it's not up there. We get into this idea of contrasts and post hocs. Okay, contrast and post hoc test. What's a contrast? What's a contrast? Contrast is a comparison of means. Okay, a contrast is a comparison of means, and that's in the notes, and we'll look at that after the formal definition. It's a comparison of means. Well, give me an example of a contrast. mu1 versus mu2. mu2 versus mu3, etc. Okay? Comparison of means, but I can actually make the contrast more complicated so that that comparison of means is actually contained in a wider framework. So you can say the contrast is a comparison of means, but watch what we can do now. What if I wanted to, I had a theory that those in the third group had a mean difference different from these two groups, okay? So what if I had the theory that those receiving 3 milligrams of melatonin had a different mean than those receiving 1 and 2. That's still a comparison, right? That's still a comparison. That's still comparing this mean to another mean. But the contrast is defining the groups according to what? Well, what's going to make you do this contrast? Based on theory, right? Based on theory. So this thing here, you're saying, you know what? I think those who received 3 are going to be different than those who received 1 and 2. Now, when would this be appropriate to do this type of contrast? Well, I'm pretending like I haven't looked at the data, right? I'm pretending like I haven't looked at the data. Before I collect the data, I theorize that 3 is going to be different than 1 and 2. Now, why is that important? I mean, let's think about that for a second. Why might that be important? Why did I have to say this idea of contrasts before looking at data? why before looking at data? Well, if I say mean 3 is gonna be different than mean 1 and 2, why don't I just look at the data? Why don't I just look at the data, then I can see, well, no, this mean is actually bigger or smaller than mean 1 and 2. What's the relevance of this? This distinction we're talking about, you're gonna see the difference. Some of you know what post hocs are. You're gonna see what a post hoc actually, the purpose of it is, because this difference in contrast of post hocs is going to depend on this idea, whether you look at the data or whether you set it up before you look at the data. So, if I set it up before looking at the data, what's the difference compared to if I look at the data first? I mean, look, if I theorize this before looking at the data, that's interesting. If I look at the data, then theorize this, how impressive is that? You know, you go tell your supervisor, you say, look, I obtained the data, I looked at it, I got a really good hypothesis. Mean 3 is different than mean 1 and 2. And present that for your thesis defense. Collected the data, I looked at it, and I theorized afterward that mean 3 is different than mean 1 and 2. How's that sound? What's the problem with that? Okay, so, and playing around with this, I go, I theorize that the marker will drop, right? So I look at it first, theorize that the marker will drop. I look at the data and I go, oh, I theorize that this mean in the population, these are sample data, in the population will be different than these two. Is that impressive?
No.
Not really. Your committee's gonna go, that's not really scientific, right? You're not really making a prediction, you're just going by what's there. You know, I theorize that if my dog eats this bone, he's gonna be sick tomorrow. Ah, he was sick tomorrow. That's interesting. I told you he would be. That's different than feeding him the bone and then tomorrow going, you're sick, there's my theory. Right. This idea of before looking at the data makes you a little bit more of a credible scientist because you're making predictions based on what? You know, you're making predictions based on not the immediate data, but what? Yeah, your experience, what you predict as a scientist, right? What you predict as a scientist. Look, if a meteor struck the Earth tomorrow and the scientist came out, we predict that the meteor's gonna hit the Earth. You know, we predict, we theorize that the meteor hits the Earth. We say, yeah, could you have told us that yesterday? If they say yesterday, they go, you know what? Or say, you know, years ago, they say in 2030, a meteor's gonna hit the Earth, and it does. Wow, they're pretty good. So we need to, let's take a little break. We need to distinguish between this idea of before looking at the data and what's gonna be the other one. If it's not before, it's when? It's post. It's post hoc. Okay, and there's a big difference between the two, and we'll talk about that after the break.
Hey, are you going upstairs?
Yeah.
Friday afternoon.
Amy,
Can we use some nice mic?
Oh, yeah.
Like, was screaming yesterday. The 368 one. I just want to buy a new one for that room. Actually, want to just like refurnish it, renovate it.
Sorry.
Over spring break. That'd be so fun.
Oh, that'd be so fun. Wouldn't it? Because then we can actually like
Yeah.
enjoy it.
Thank you, my dear.
Fridays.
My dear.